All right. So we have introduced the embarrassing parallel computation and divide and conquer. And today we will talk about pipeline computation and synchronous computation. Okay. The other two, commonly seen parallel computing methods. Okay. All right. And again, we will use three examples to show how you can use parallel computation. And different from what you have learned probably before about about pipeline computation is that actually there are three types of pipeline computation, and we will explain how they are different. Okay, so but in general, I think this is what you know about pipeline, right? Which is right, a strategy that divide uh, your computation into a series of tasks, right? And each of those tasks can be completed independently. So you can ask, right, multiple processes to handle each of the tasks. And so that means you can use more computing power on solving the single problem. Okay? And specifically, we often see it from industry, right? Manufacturing. That's the best way to, for mass production, right? We all know that, for example, like, to manufacture a car, we can divide it into many stations, right? Maybe this station is to install the door, the next station install the engine, and the next station try to paint the color, etc. So we can divide it into many stations, right? And all those stations can manufacture the car at the same time. So if we have more station, we can utilize more computing power or human resources. Okay. So anyway, that's that implies, right, we can solve the problem in a shorter time, or solve the or provide higher throughput, right? And we can complete more tasks within a given time. Okay. However, actually, that's just one type of pipeline computation, and usually the easiest one. Okay. So the first type of pipeline computation is the example we mentioned in manufacturing. Okay? In that case, if you look more carefully, you will find that for that kind of problem, you actually try to solve the same problem um, by multiple instance, right? Like manufacturing, especially for mass production, we basically try to manufacture the same item for huge quantities, right? So, like manufacturing a car, we have to build thousands of cars. Okay, so for that case, it's very easy to use a pipeline because we have so many cars. So each car can be built at each station, and we can have many stations as long as there are more cars to build than the number of stations we have, right? So for manufacturing, that's the pipeline strategy we use. Okay. However, it may not always be the case, right? May not be the case that we need to build, or we had to solve the same problem for multiple instances. Sometimes we just need to solve one problem, one instance, right? We try to use pipeline to accelerate the computation of solving a single problem instance, such as sorting again, right? We want to solve the sorting problem on a given array with more processes. Okay, in that case, we only have one problem instance. So obviously, we cannot just apply pipeline in a trivial way like the first case. Okay, so usually in the second type of pipeline, we only have one problem instance. However, when solving this problem instance, we might apply multiple operations on each of the item, the data item in that problem instance. So there are some opportunity for us to use pipeline to accelerate the computation. Okay, so we will see an example later on. Okay, the third type of pipeline is even further away from what you have in mind for pipeline, because in general, right, by default, when we talk about pipeline, you will probably thinking about the fact and the limitation that the problem or the computing task need to finish one task at a time, right? They cannot be overlapping, right? You have to solve the task at one stage or one step at a time before you move on to the next stage or phase, right? Or step. Okay. However, for the third type of pipeline, it actually allows the computation between different stages to be overlapped. So, which means it's possible that even further reduce the overall computation time because those pipeline stage can be overlapped to each other. Okay, so if this happened, then this is a special case and it classified as a third type of pipeline here. Okay, so this is less trivial, right, and less commonly seen, but again, we will show you a concrete application, right, to show you that it actually exists. Okay, all right. So the basic form for those three types of pipeline computation. The first type, as we mentioned, is by definition, it requires multiple problem instance. Okay, such as you build multiple cars, or you try to sort multiple arrays, not just a single array, etc. Okay. In that case, as we all know, basically we can divide our computation into multiple tasks, right? Independent tasks. Okay, and each task we will assign it to one process to do the computation. Okay, and we have multiple instances. So for each instance, along the time, you will go through each of those step or stage, right, in order to complete all the computation it needs. Okay, and ideally, right, we also know that the computation time for each stage must be the same, because you have to complete the first stage before you can complete the next stage, right? And when the instance is doing for example, handled by process one, then process zero can try to compute the step one for instance two, right? So on and so forth. We all know that's how we can overlap the computation among those instances. Okay. So as long as we can, right, make sure all the processes are busy and doing computation, then we know supposedly we can increase the throughput, the overall throughput of this computation, right? Because all the processes, they are busy, they are producing results. Okay, all right. So, however, that's the case if all the processes are busy. So we all know that for pipeline, especially this type 1 pipeline computation, to be efficient, then we need to make sure the pipeline is filled, right? So in other words, if you have P processes, or that means you will have P stages, and it requires P minus one, right, time intervals to fill up the pipelines. And after the pipeline is filled, then we know that what happened next is every time interval, we will complete the computation of a problem instance. Okay, so basically we have this linear throughput. Okay, so in other words, the parallel efficiency is not ideal before the pipeline is filled. So that's why usually we have to have more problem instance, right, than the number of processes. Okay. And so that's the requirement for type 1 pipeline. Okay. So its efficiency depends on the number of problem instance you need to solve. Okay. And however, this strategy is very easily, it can be implemented very easily because given any sequential code, of course, we can arbitrarily divide it, right, into those sequence of tasks. And so it's very easy to write this parallel code. Okay. However, the difficulty is we need to make sure the load, right, the computation time of each stage is roughly equal. Otherwise, of course, there will be some idle time, in between, right? So that will also reduce the parallel efficiency. Okay. Right. So that's type 1. So how about type 2? So type 2 looks very, very similar, or you could say exactly the same as before. The only difference is you can see here every computation task is coming from the same problem instance, but it is a computation applied on different data item. Okay, so imagine this computation, right, involves some series of operations applied on this data array, right? Then at the first time interval, the process 0 will try to compute the applied operation on the first item. Okay, and then in the next time interval, process 1 will continue to apply the operation on the first item, while the P0 can now apply the operation on the second data item, so on and so forth. So assuming all the data item needs to apply those operation before its computation completes, then similar to before, right? We can obviously see that we could explore parallel computation power in order to reduce the overall time to finish all the computations. Okay? So the efficiency of this parallel computation, again, depending on the how many data items you have versus the number of processes. Okay, so the data items should be more than the number of processes. Okay, all right. So how about the third type of pipeline? The third type of pipeline, as we mentioned, it referring to the case that you actually even can overlapping the computation time among those stages. Okay, so as you can see over here, of course, it's still a pipeline computation. So you can imagine the later stage cannot start earlier than the previous stage, right? It's impossible in pipeline computation. However, the later stage can start before its previous stage completed. So we can still create this overlap between the computations in order to save some time, right? So this is what we call the type 3 pipeline. Okay? And also you can see the example on the right side. We have restriction on the start time. However, we don't have a restriction on the end time, right? So in some case for type 3, it's even possible that some later stage is completed before the previous stage. Also, well, this case is more rarely seen, or it require less data dependency in the computation, but this case could still be happen. Okay, so anyway, for type 3, is more emphasized on the fact that the computation between stages can be overlapped, and as long as their starting time still follow the order of those stages. Okay. All right. So we will show you example for type 3. So you will see why it could happen. Okay. All right. So we use 3 examples to illustrate those 3 types. Okay. So the first example is for type 1, which is quite easy, right? So for example, we want to add the numbers of array, right? And if we use a pipeline computation, that means like this, we will have, if we have n items, then we probably have n processes. Okay, and each process will only try to add a single value to the result, right? And so if we have some initialized as 0, when it goes through those additions at the end, it will get the result, right, of the sum. Okay. So obviously, this case, if we implement the computation like this, then we actually don't see any performance acceleration, right, or any benefit from it if we only try to add the summation for a single array, because obviously it is exactly the same as what happened from a sequential code. Okay. However, imagine you have more arrays to solve, right? Say you have A, B, C, D, E, F, G, multiple arrays to do the same thing. Then it will be different, because when the process one try to add the item for the first array, for the first array, process 0 can start adding the value for the second array, right? So if we have more arrays to add, then of course this simple pipeline strategy can still utilize the parallel power, computing power, right? But you need the multiple problem instance in order to see the benefit. Okay? And this type of pipeline, of course, in terms of the implementation, is quite trivial, right? We basically only need to take care how to pass the data or the problem, right, to the next stage. So if you are using the MPI, right, then basically just have those send and receive code, right, added into your payroll program, right? So you can pass the information needed for your computing task to the next stage or the next processes. Okay, and of course, for the first process, you won't need to receive anything, right? You start from scratch, and for the last one, you only need to receive the result, right? It doesn't need to pass the result to the next process because it's the last one already. Okay. So combined with the single program multiple data programming model, we know that we can use a branch, right, to identify whether it's the first process or it's the last process. So it can adjust whether you need to call send or receive according to it. Okay. All right. So since all of you have complete homework 1, I think it should be quite trivial for you how to implement it, right? In MPI or other parallel languages. Okay. All right. So then we move on to the second example. This is the example for the second type of pipeline. So as you can see over here, we try to use a pipeline strategy to accelerate the computation of sorting a single array or single numbers. Okay. And this algorithm actually is the same as the insertion sort. Okay, so the pipeline strategy for payroll sorting, as we introduced here, is actually the same as the insertion sort. You know that. Okay. So what's insertion sort? I believe most people, at least including me, using this kind of sorting when we play poker. Right? We usually just scan from the first card, right? And try to see whether there are smaller or larger number than it, right? And then decide the position of that number. And then check the second number, the second card, and then the third card. And just always try to insert it to the right position, one at a time. Okay? That's insertion sort. And as actually that's, if we do it in parallel, then it's actually a pipeline computation. Okay, so let's see what happened. Okay, so for example, here we have 5 numbers. Okay, so by definition of insertion sort, what happened is at the beginning we have nothing to be sorted, right? So when we see the first card, is the only numbers we know. So of course, it will be placed in the first position. Okay. And then we look at the next card is 2. So we compared it to the number we have sorted, which is 5. In this case, we try to sort the number in decreasing order. So we know 2 should be right next to 5. Okay. Then we check 1, and we can 1 will compare with 5 first, and you will find 1 smaller. So we'll continue to compare with the next card, which is 2. It's again 1 smaller. So we push 1 further back to the third position. Okay. And then why this is why we called it insertion sort, because for the next card 3, right? We will find it smaller than 5, larger than 2. So we will insert into this position, right? And it will be his right insertion position. Okay. And so on and so forth. As you all know, we will just keep repeating this, try to insert the number to the right sorted position. And at the end, after we insert the position for each of the card, then we have a sorted array at the end. Okay. All right. So why it's no, if we want to parallelize the insertion sort, pipeline will be the best fit for you. Okay. And the reason is, as we're showing over here, right? You can imagine we have if we have n numbers to sort, then we use n again, n processes. And each process, its task is to receive a number and compare the number with the number he originally held. Okay. And then do a comparison between the new card and the old card. Then move the card with a smaller number to the right side or to the next tasks or next processes. Okay. And we simply keep repeating this operation for each of the processes. And then, as you can imagine, what happened is those processes will always try to push the smaller number to the right side, right? And the number will be inserted into this compare and the swap operation in order, one by one. Okay? So for example, at the beginning, everything is empty, right? And we start to put the first number, which is 5, to P0. And P0 has nothing, so he will keep 5 over here. And next is 2. When 2 comes, and P0 will compare 5 with 2. If it's no, so 2 is smaller, so it will push 2 to P1. Okay, so so that's why you can see 2 will propagate it to P1. And for the next instance, if 1 counts, then because P1 is empty before he received 2, so of course he simply just store it. But then if we have next number 1 comes in, as you can see, 1 will compare to 5. So again, he will push 1 to 2, while process 1 will compare what he received to his current number again. So as you can see, the numbers will just pipeline into this these stages, right? And one by one propagated to the right side. Okay. All right. And when they propagate to the right side, all the processes do the compare and swap at the same time. So those numbers can be shifted to right simultaneously in parallel. Okay. And of course, the comparison will also be done in parallel. Okay. So at the end, of course, imagine the worst case, right? The worst case is that say the smallest number is entered to the pipeline at the last step, at the last time, at the end, right? So you need n, right, all of n to basically wait until that number entered into the pipeline. And that number need to be pushed all the way to the last processes. So the overall time, right, the overall complexity, even though it's in parallel, should be all of 2n. So in short, is O of n. Okay, all right. So the O of n complexity actually is not bad, right? If you record the parallel merge sort or parallel quick sort, etc., most of the parallel sorting algorithm has have the complexity of O of n. So even sort insertion sort, with pipeline, we can again achieve the same complexity. Okay. But however, of course, it's if you consider the constant is 2 by n. So in terms of the actual runtime, it could be slower. However, in terms of the complexity, it can still reach O of n. Okay. All right. So this is a type 2 because we are simply use pipeline to do the computation on a single problem instance. Okay, and we are still able to achieve a speed up, right, from or acceleration from O of n log n to O of n. Okay, right. So lastly, we will introduce the linear equation solver as example for the type 3 pipeline. Okay. So what is a linear equation solver? This is a special case, actually. As you can see, it's a special case where the linear equation is upper triangular, means that you have 0 for the bottom half triangular. Okay. This is a easier case because as you can see below, right, we can easily solve this equation by exam from the last row, right? Last row, also we have say n variables, right? But for the last row, we only need the value, need to know, you only involve x0, right? So obviously, according to the equation, it tells us a00 multiplied by x0 equal to b0. So obviously x0 equal to b0 divided by a00, right? So we can get the result, the value for x0 first. Okay, simply use the last equation. Okay, and then we can iteratively, right, use the result of x0 to solve the second to last equation, because in that case we only have x1 to be the unknown value. So again, we can easily get x1 and so on and so forth. We can solve those equations one by one to get the result of each of the variable. Okay. So that's what we mentioned, right? This is what we call the back substitution method, right? We solve from x0, and then we use the result of x0 to solve x1, and so on and so forth, right? And we can see that we actually can, come up with a general form like what we see over here, right? For to compute the result, the value of any xi. Okay. However, in order to solve xi, as you can see over here, he needs the information of the unknown variable before it, right? From 0 to I minus 1, because its computation involved those unknown values. Okay, so we have to solve them one by one. Okay. All right. So how can we use pipeline to do this? Okay. So similar to before, here we have each process. Try to solve the value for each unknown variable from x0 to xn. Okay. And as you can see over here, if you think in a trivial way or naive way, then what happened is P0 will solve the last equation and get the result for x0. Then pass the value of x0 to P1. So P1 can continue to solve the result for the value for x1, and so on and so forth, right? You can see we have to pass all the previous results to the next processes in order to compute the next unknown variable. Okay. And at the end, of course, we will receive all the unknown processes, all the unknown variable, and then be able to solve the last x value. okay, and finally output all the results. Okay, all right. So this computation is a pipeline because we have to solve those variables one by one. Okay, and in this naive solution, you can see again it follows the pipeline. What we know about the basic pipeline, we have to wait, right? P1 have to wait P0 before start its computation, and P2 has to wait P1 to finish before P2 can start. Okay, but it's actually not necessary, right? Because as you can see over here, we can actually overlap the result, the computation among those stages. Because you can see the later stage always involve the computation of their previous variable. Okay, so if we can pass those information to the later stage in advance, then the later stage can start computation earlier, which means like P0, right? After he complete the get the value for X0, he actually can broadcast or just simply forwarding the value of X0 to all the downstream processes, right? And then all the processes can already start doing the computation because their computation is a summation over all the the variables. So if you already know the value of X0, then even for P3, he can immediately start the computation involve X0. Okay. So what happened is as shown over here, right? Because according to the equation, again, over here, you can see every process, he tried to add the value from X0. So as soon as he received X0, then even for any arbitrary Xi, he can start doing this prefix sum computation. Okay. All right. So that's why if we can implement this pipeline as shown in the left side. Okay. For every process, of course, at the beginning, this is the sequential code, right? We just for loop, right, to add it one by one. Okay, but in parallel, we can it goes to do to get the prefix sum, right? So starting with 0, and after he receive the any x value from his parent or upstream processes, he can already do the summation, right? By multiplied by multiplied it by the coefficient of that x value, right? And of course, we don't want to delay the image forwarding, so information forwarding. So after he receives, he will actually just simply send it to the next process before he does the computation. So that's why we can overlap the communication with the computation. Okay. So what happened is because broadcast is slow, right? It's not scalable. So here we can also use the pipeline to forwarding the message, okay, forwarding the information, and make sure all the processes can receive the information and start do the computation before his previous process is complete. Okay. All right. So anyway, this is what we could implement it to realize what we described. And after we get all the summation, we divide it by the coefficient again, according to the equation, right? And get the value of xi for pi. And again, after he get the result of xi, he will send the result to the next processes. Okay. So overall, at the end, you can see the communication can be perfectly overlapped by the computation, right? Or at least the computation from the previous stages. So the only additional computation time from each process is this computation alone, right? It's only out of one time. So since you have n processes, so the overall complexity of this pipeline implementation is only out of n. Okay. If you don't, right, on the other hand, if you don't overlap the computation, you will find that the complexity is actually O of n squared. So actually, you can greatly reduce our computation time, okay, in this case. Okay. All right. So that's an example of a type 3 pipeline. So you can see that for some computation, when you apply pipeline, it is possible to overlay layer computation time if there is some information that you can pass forward and without right causing any data dependency issue. Then the computation for the later stage can be overlapped with the computation of previous stages. So you can reduce the complexity and certainly reduce the overall computation time. Okay. All right. Okay. So that's pipeline. Okay. We have 10 more minutes. So let's have an early break now, and we will start at 4:20 and start introduce the synchronous computation.